Okay, hello everyone. This video going to show you explain the problem, one of your problem in your homework. Okay, I will explain this problem 11.1161. This problem. Okay, but this problem I won't do it thoroughly. Okay, I only just explain part of the problem. Okay. Okay, he say, yeah, this is a beam and this is the shape of the cross section of the beam. And then he say if the beam is subject to 3 kilonewton meter moment, determine the resultant force. Yep, there's a very special point. There's a special point in this problem. He say determine the resultant force. You say determine resultant force or the bending stress acting distribution acting on top of radical board. Okay. And maybe the problem description is not very clear. Yeah, so let me explain. He want you calculate resultant force at this surface. Okay, this one. He want to calculate resultant force. The problem want to calculate resultant force acting on this surface. Okay. A resultant force acting on this surface. Okay. Okay, so that's the. I think it's much clearer. Maybe the word description here is not very clear. Okay, you want to calculate resultant force acting on this surface. How to calculate resultant force? You might think very strange. So let's draw the schematic picture. So he say, mm-hmm, this is here. This is 25 millimeter. Okay, and this 100 millimeter. Okay. Okay, and previously we said in the bending stress. Okay, in the bending stress. Okay, if this is a profile, it's hard to draw a straight line. Okay, this side view of the beam, and if it's a neutral axis here, okay, and for the bending stress, if there is a moment like this, you will have a distribution of shear stress, right? Distribution of shear stress. Okay, and up. If this moment up is compression, and down is extension. Okay, okay. Okay, so you see here is a distribution. Okay, for a bending stress, you see here is a distribution of the stress. Distribution of the stress. Distribution of the stress. Okay, stress. Okay, so they're very interesting. The problem here, you want to calculate the resultant force. Okay, how to calculate resultant force? Do you remember that? Okay, in the previous in the I think in the first half of this semester we say, oh, okay, if there is a beam here, okay, and then I have distributed loaded, okay, okay, and then there's a problem. Okay, what is FR? Okay, determine the resultant force of distributing load. Okay, and in that case, in this problem, the distributing load. Do you remember the unit? This is W of x. Okay, W of x. Its unit is it's Newton. It's force per meter. Okay, force per meter. Force per meter. Okay, let's call force intensity. The distributed load is the distributed load W is the force intensity. Is force divided by meter. And how to calculate resultant force is area under the curve, right? Under the curve. Okay. And here, yeah, you have to calculate resultant force. Okay. Yeah, because we have a force intensity distribution. Okay, we have force intensity distribution here. Yeah, but be careful because here, okay, in the bending stress calculation, we have the stress distribution. Okay, So how to translate the stress distribution to the force distribution? Okay, how to change the stress distribution to the force intensity distribution? Yeah, yeah. So that's the I think that's the final key, the key of this problem. Yeah, we have a shear stress distribution. Okay, but we want to translate to the W distribution. Okay, force intensity distribution. So how to do that? Okay, so first of all, we still have to calculate the shear stress at the bottom and the top. Okay, so and here I won't calculate again. Okay, I think you can calculate by yourself. You can using the what is called minus my over I. Okay, so we will have the distribution. Sorry, we have at the bottom we will have the compression stress. I think yeah, I won't calculate. You calculate by yourself. I just give you the answers. 1.979 megapower. Okay, and at the top we will have the 114.94 megapower. Okay, and here we will have the distribution of shear stress. Distribution of not sorry, not shear stress, distribution of bending stress. Okay, so we have distribution of bending stress, and okay, the next thing is how to translate to the force intensity distribution. And so at the very beginning, okay, we can okay, this is a bending stress, this is the stress, right? So for the stress, okay, time the area we can time the area to become a force, right? Okay, what's the area? It's well 100 times 10 to the power minus 3, 25 times 10 to the power minus 3, and you will have the force. Okay, you have the force. Okay, you have the force. So it's Newton. It's Newton. And the same thing. This is a button, and the top 14.94 times 10 to the power 6, and you times the area. You times the area. Okay, times the area, and you will have a force, right? Okay, force. Okay, okay, force. Okay, force. Okay, but be careful when we do the calculate the resultant force. Say we say it's area under the curve. Okay, and Wx is force intensity. Force intensity. It's force intensity. Force intensity. It's not a force, it's a force intensity. Okay, that means the force per meter. And so we have to convert this force to force per meter. Okay, and how to convert? Okay, no, so we finally we want to the force intensity change along this vertical line, along this vertical line. So you have to divide it by so you have to divide it by the length. Okay, you have to divide it by this length. Okay, you have to divide it by this length. So you have to divide this. You have to divide this. You have to divide this, and then you will become a force intensity. Force intensity. Okay, so it will become like this: 1.979乘10⁻⁵乘15乘10的复杂. Okay, here is 14.94 times 10 to the power 6 and 10 times 25 times 10 to the power minus 3. And then you got a force intensity at the bottom and at the top. Okay, this is a force intensity. It's a bottom and this is the top. Okay, you got a force intensity, and you have force intensity and calculate this area under the curve. You will get the resultant force. Okay, be careful. So the key of this problem, yeah, you have the bending stress distribution, and you want to convert the bending stress distribution to the force intensity distribution. Okay, so we will start from very beginning. So we have the bending stress, and you times your area equal to it will become a force. Yeah, but what you want the force intensity, so you have to divide it by the length, divided by the length. Okay, so So you have a force intensity at the bottom and force intensity on top. And okay, so let me erase here. Okay, so how to finish? So let's finish this calculation. Okay, so at the bottom you have the 1.979 times 6 times 25 times 10 to the power minus 3, and here you will have 14.94 times 10 to the power 6 times 25 times 10 to the power minus 3. Okay, and then we calculate the area of this trapezoid. Calculate the area of this trapezoid. So how to calculate the area of trapezoid? Okay, don't forget. Okay, it's base up bottom up base at the bottom base and times the height divided by 2, right? OK，上底加下底乘以高除以2。OK，1.799 979 times and this is bottom and this is top. 上底加下底 upper base upper down bottom upper base and bottom base at and times the height. What's the height? The height is here 100 millimeter and divided by 2. So that will be your answer. Okay, let's see what the answer will be. Okay, so 1.979 and plus 14.94. Okay, times 10 to the power 6 times 25 times 10 to the power minus 3. Okay, and times 100 and times 10 to the power minus 3 and divided by 2. Okay, and okay, so you will get 121.15 and it's kilo Newton. Okay, that's the resultant force acting on this surface. Okay, so once again, okay, in bending stress, we have bending stress distribution, but we want to calculate the resultant force acting on this surface. So we need to translate the bending stress distribution to the force intensity distribution. And then we calculate area on the curve on the distributed loaded, and we'll get a resultant force. Yeah, don't forget how to calculate the resultant force. Okay. Okay, so just start the video here. Okay, and see you in another video. Bye bye. Yeah, 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 yeah.